is to start off with a little preamble. This is not part of the update to the DART mission. Has to do with upcoming anniversaries and things of that type that I thought would be very appropriate for the membership to know about. The first thing I'm showing here is not a USA project. This is an ESA project, European Space Agency. What they're doing here with this mission called JUICE is sending a spacecraft to orbit one of the moons of Jupiter. That moon is Ganymede. And the reason I'm bringing this up right now is the launch of this spacecraft is coming up in about a month. I'm sorry, not the launch, but there's going to be an encounter with the Earth-Moon system in about a month. It was launched on April the 24th of last year. And it's the first interplanetary spacecraft to the outer solar system planets not launched by the United States. It's the first spacecraft to orbit a moon other than the Earth's moon. That's Ganymede, one of the Galilean moons of Jupiter. It has 10 science instruments on board. It will be braking. Well, this is called a braking maneuver that's coming up next month. Usually when you have a spacecraft that is going different places in the solar system, you'll design a maneuver to come close to a planet to get a boost from that planet's gravitational field. This one is different. This is going to actually come close to both the moon and the Earth, not to speed it up, but to slow it down. It's a double world first. The first ever lunar Earth flyby. The first ever double gravity assist maneuver. It will fly past the moon on August 19th. It will come within 700 kilometers of the surface of the moon. And the very next day, August the 20th, it will fly past the Earth, and the closest approach will take it to about 6,807 kilometers above the surface of the Earth. It's going to be flying directly over Southeast Asia and the Pacific Ocean. I'm not too sure if we're going to be able to see any of the spacecraft trajectory from Southern California, but it will be in the afternoon, Pacific time. And I suspect that maybe with a large telescope, there might be a chance. I doubt that any of us amateurs will be able to see it because it is a daytime flyby. But it's something I think you might want to check up on the internet to get more information on. After its encounter with the Earth and the Moon, it'll be flying on to Jupiter via Venus. So that's the reason for the slowdown or the deceleration or the braking maneuver, is to slow it down to bring its orbit around the sun to come into the Earth's, within the Earth's orbit, fly back by Jupiter and get a gravitational assist from Jupiter to boost it out to the outer solar system. That maneuver with Venus will be in August of 2025. That'll be next year. There will be 2 more flybys of the Earth, one in 2026, another one in 2029. Arrival at Jupiter in 2031, and orbiting Ganymede in 2034, about 10 years from now. Okay, Gary. This shows just a little bit of the maneuver. If you look over here on the left-hand side, you'll see the position of JUICE on June the 24th. Right about now, it'll be right here at this particular bullet near the middle. And then, like I said, there'll be a moon flyby on August 19th, and the next day, flyby of the Earth. Okay, Gary. Okay, tomorrow is a special day, as everybody knows. Tomorrow is Moon Day. But it's an extra special anniversary of Apollo 11. This is going to be the 55th anniversary of the first man landing on the moon. Okay, Gary? This obviously is the Apollo 11 crew patch on the left and the Apollo 11 crew on the right-hand side. They don't need any introduction. Everybody knows who they are. That was one special day. Go ahead, Gary. And everybody knows what these pictures are too. These have been seen by everybody on Earth thousands and thousands of times, right? These are very historic. You would think that with the history of these photographs, everybody on Earth would have seen them many times, but that's not the case. The picture on the left is the very first picture taken by a human being while on the lunar surface, but inside the lunar module. It was taken at 5:32 p.m. Eastern Daylight Time, July the 20th. And a few hours later, the picture on the right was taken. That's the very first picture taken by Neil Armstrong after he stepped on the lunar surface. So those are very historic. If you're wondering what this bag is on the left-hand side of that picture, that's a jettison bag, better known to most people as a trash bag. Okay, Gary. 30 years ago, Mother Nature put on a 21-gun salute to commemorate Apollo 11 landing on the moon. The 21-gun salute consisted of 21 major fragments of the comet Shoemaker-Levy 9 comet. The first impact of those fragments occurred on July the 16th, the 30th anniversary of the launch of Apollo 11. The last fragment was hit Jupiter on July the 22nd, just 2 days after Neil stepped on the surface of the moon. And this is a picture, I think this might have been taken by Hubble. It shows, you know, the 21 fragments. And the next slide will show them a little bit better. I have them numbered right here. They're numbered 1 through 21, and they also have letter designations also. The very first one that hit was number 1 over here. It's called fragment A, and that hit at 60 kilometers per second, reached a peak temperature 24,000 Kelvin, and let's see. Oh yeah, it says the plume from the fireball reached a height of over 3,000 kilometers. The biggest fragment was fragment G. That's labeled number 8 over here. And that is the largest, when it hit, it was the largest explosion ever witnessed by humankind in history, except for in the solar system, except for the mass ejections from the surface of the sun. When that fragment hit, it released an energy equivalent to 6 million megatons of TNT, which if you don't know what that means, just talk to Richard the next time you see him. He knows all about those things. But it's 600 times the world's nuclear arsenal energy. It just gives you an idea of how violent that event was. Go ahead. This is an infrared picture that was taken after the fragments hit Jupiter. You can see with the whitish ovals here where the particles actually hit. Those in visible light, those really turned out to be black, and they were visible in amateur telescopes. So very apparent. And I think that that those lasted for up to about a week. Okay, Gary. And 95 years ago, on July the 17th, which is just a few days ago, 1929, Robert Goddard flew his fourth liquid-fueled rocket, and that was the very first rocket to carry a scientific payload. And among the instruments were a barometer and a camera. And this is a picture of it. This is a refined version of the rocket that he had built and launched back in 1926, which was the first liquid-propelled rocket ever flown. Okay, and this now starts my presentation on the update to the DART mission. I've given a presentation on this several times. This is basically originally supposed to be just an update, but for the benefit of everybody who did not see this, I'm going to be giving a little bit more than just an update. I'll be giving some prior information that I've given before, but there's going to be a lot of new information here too. To give you an idea of the environment that the Earth has here in the solar system, here's some statistics for you. Each day, over 100 billion meteoroids, micrometeoroids, and other space debris with masses larger than 1 microgram enter the Earth's atmosphere. That's a lot. That's 48.5 tons of meteoritic material that falls on the Earth every day. 10 to 50 of those objects are larger than 10 grams that actually go as far as reaching the surface. Okay, Gary. Now, if you're planning to go to the International Space Station anytime soon, you do not want to see this. Just close your eyes, because what this shows is the location of all the bolide events that have occurred from 1994 to 2020 or 2013. The blue dots on here indicate the bolides that entered the Earth's atmosphere at night. The orange ones are the ones that entered during the day. The size of the dots indicate the energy of those events, going from 1 gigajoule all the way up to 1,000,000 gigajoules. And superimposed on this, I have, just to give you a feel for how much energy these are, I show the energy of the Hiroshima bomb little boy that was dropped in 1945, along with the amount of energy released at Chelyabinsk back in 2013. As you can see, Mother Nature does not discriminate. She has no favorite country or hemisphere. She has no favoritism about whether it's the north latitude or south latitude or east longitude or west longitude. These are spread pretty much evenly across the across the world. Okay, Gary. Now, I thought I'd show this chart in here too. This is kind of interesting, I think. It shows all the asteroids larger than about 50 meters in diameter that are known to have missed the Earth by less than 1 million kilometers. Now, you think that maybe 1 million kilometers is a pretty long distance, but you have to remember that the moon is only 384,000 kilometers away. So this is basically a very near miss in astronomical terms of these objects coming close to the Earth. To give you perspective on this, when it comes to 50-meter diameter, the estimated diameter of the object that hit Meteor Crater in Arizona, also called the Barringer Crater, was estimated to be about 30 to 50 meters. So you get an idea of how much damage something of, could have produced here by looking, just remembering how much damage that event was. One thing I'll point out here is this one that's highlighted in yellow near the bottom, March the 22nd, 1989. Actually, and I don't know why it's March the 23rd, that is National Near Miss Day, but I suspect that even though it's shown as an event that happened on March the 22nd, that may have been US time. It may have been March the 23rd Universal time. But anyway, that's called Near Miss Day. And the object that came close to the Earth on that day was Asclepius, which was discovered on March the 31st, 9 days after that event. And it was because of the fact that they found out that such a large object of that type coming so close to Earth wasn't even known about until 9 days later, that they knew that they needed to come up with some system to make sure that we would be able to know in advance when a large object like that would come close to the Earth. And that's what got things started, basically. Here's another chart that gives you some information here on the impact hazard from asteroids. I have 1, 2, 3, 4, 5 different columns for objects, asteroids in particular, of different diameters, going from 4 meters to 25 meters, 140 meters, 1 kilometer, and 10 kilometers in diameter. For each one of those objects, I have listed the size of the asteroid. Asteroid size, the frequency at which you would expect an object like that to basically come close or maybe hit the Earth. Tells you a little bit about the impact, the number of near-Earth objects of that size, the percent of those objects that have been discovered so far, the mass, and the impact energy. Superimposed on this, I have 5 different arrows numbered 1 through 5. The first arrow is about the energy yield of the Hiroshima nuclear bomb. The second one is Chelyabinsk. The third one is the Barringer crater or meteor crater in Arizona. Number 4, 140 meters, about the size of Dimorphos, which was the target for the DART mission that I'll be talking about. And then I wind up here with number 5, which is about the size of the Chicxulub object that wiped out the dinosaurs about 64 million years ago. I should say not all dinosaurs, but all the non-avian dinosaurs. Here's some statistics on near-Earth objects. These are objects that come fairly close to the Earth and should be paid more, close attention to because of the fact that they are near-Earth objects. There's a total of 35,295 of them. They consist of not only asteroids, but also comets. Of those, there's 10,912 of them that have a diameter of over 140 meters. And as you can imagine, those objects can do a lot of damage. Unfortunately, the bad news is that only 42% of those objects have been found. There's still 15,000 more to be discovered. That's the estimate anyway. There's also a category that have been singled out as being potentially hazardous. and those number 2,425. Those are the ones that we really are most concerned about, because their orbits actually cross the Earth's orbit, and they could in the future be an object that could actually hit the Earth. Okay, next chart. Okay, and here's some facts about the mitigation of the asteroid threats. The impact of a near-Earth object is the only large-scale natural disaster that can be prevented. That's something to think about. We actually now have the capability to prevent a natural disaster that could do us in. We don't have to rely on Mother Earth. As I should have pointed out at the very beginning, the Earth has two oceans. It's got a water ocean and it has an atmospheric ocean. And the atmosphere is the one that has protected us pretty well from all these objects that are entering the atmosphere. The problem is that it's good only up to a particular point. Once you get up to about a 30-meter size object, you have to rely on just luck, or maybe your intelligence by building a defense mechanism to protect you. And those are the objects that I'm going to be addressing here today. There are actually 4 different methods, basic methods that can be used to defend us. There's nuclear options, there's kinetic impactors, gravity tractors, and civil defense. I won't go into any details on any of them except for the kinetic impactors, because the DART mission was actually designed to test out that particular method of mitigating threats from asteroids. Kinetic impactors are adequate to prevent impacts on the Earth by moderate-sized near-Earth objects with decades of advanced warning. What's important here to know is it's very important that we have a system in place, if this system is going to work, that will be able to detect an object that's going to hit the Earth years and years in advance. So what that means is early detection and precise orbit determination are the keys to reducing the delta V required to alter the impactor's orbit. An impact on an asteroid by an impactor is going to do one thing. It's going to produce a delta V on the asteroid that hopefully will change its orbit around the sun enough that it's going to miss the Earth. And this is a chart that I put together. It shows all the different options that we have for mitigating asteroids. The ones on the left are the nuclear options, and the ones on the right are the non-nuclear. At the very bottom on the right-hand side is the kinetic impactor, and that's what I'm going to be addressing in this presentation. So you talk about the 4 different mitigation methods that will protect us. This shows the regimes in which each one will be able to do the job. And like I said, the one that's identified as kinetic for the kinetic impactors is the one option that we'll be concentrating on here. That's what DART used, okay? Now this is asteroid impact in a nutshell. From a physics point of view, it's very simple. Basically, it's a conservation of linear momentum. The linear momentum before the impact is equal to the linear momentum after the impact. The one after the impact consists of 2 parts. It's the momentum of the ejecta, and there's the momentum imparted to the asteroid by the spacecraft or the impactor. What's important to know here is that when you hit an asteroid, especially one that is what's called a rubble pile, what's going to happen is you're going to produce not just a delta V based on the impact force, it's also going to produce a lot of ejecta, which is going to help you out by turning that asteroid into a rocket engine. The ejecta are basically the same thing as the exhaust from a rocket engine. And as you know from Newton, for every action, there's an equal and opposite reaction. So when you have ejecta being pushed out to the left, you're going to have a momentum change with the momentum being pushed off to the right. And that's going to help. There's a parameter that is key in this whole thing. And that's the whole purpose, basically, of the DART mission and the succeeding missions, which I'll address later on. It's called the momentum enhancement factor. It's labeled as beta, the Greek letter beta. And what that is, it's the ratio of the total momentum imparted to the target from the impactor and ejecta to the impactor momentum. So it's a ratio. And a lot of times you're going to see a lot of misinterpretation on the internet about this parameter. What you'll find about, I would say maybe 7 times out of 10, they'll tell you that the ejecta momentum is equal to beta times the momentum of the impactor. That's not true. It's beta minus 1. And you'll see that many times, so you got to be careful. But the prime reason for these missions basically is to get a good number on that parameter. Here's a chart that I put together just to give you an idea of the times that are involved here. And there's a very simple thing on this chart. First of all, the chart shows you on the horizontal scale the change in the asteroid velocity from the impact by the impactor. It's called the delta V. The vertical scale is the time from kinetic impactor impact to the predicted asteroid impact on Earth. So it's a time scale on the vertical scale. It's a velocity scale on the right hand or horizontal. There are 2 things to remember here, 10 and 20. If you have a change in the velocity of the asteroid from the impact of about 20 millimeters per second, that then means that it's going to take 10 years for that asteroid orbit to change enough to miss the Earth, assuming that all you need to do is to change the location of the asteroid by 1 Earth radius. Same thing over here too. If you have a change in the delta V, or have a delta V of 10 millimeters per second, it takes 20. So it's 10 and 20 are key on this. But you can get an idea that it takes a long time for these small changes to build up to save the Earth. So that's why you need to know far in advance when you have, when you have an asteroid that might be a very big threat to the Earth. Okay, so that brings us up to the DART mission, the mission to test out the impactor method. It's NASA's first full-scale planetary defense mission to test out the impactor. Purpose was to demonstrate planetary defense technology, assess effectiveness of asteroid deflection by an impactor, and obtain accurate measurements of momentum transferred to an asteroid, beta. Always remember beta. The target was Dimorphos. The launch of the vehicle was November 24th, 2021. Impact occurred in September 2022. Okay, and this is just an artist's depiction of the impact with Dimorphos. Dimorphos is actually a moon. It's a moon of Didymus. It's a very small moon. It's a small object, but nevertheless, it can do a lot of damage if it was by itself and coming straight for the Earth. The DART consisted of 2 spacecraft, the primary one having the big wings of solar cells. There's a CubeSat called Lycia Cube that was key to this because that was the one that was used to take photographs or pictures of the actual impact of the spacecraft on Dimorphos. Okay, here's some information on both the spacecraft and the impact. Well, I should say spacecraft and the companion spacecraft here. The total mass of DART when it hit Dimorphos was 580 kilograms. That's about 1,275 pounds. That's not all that big, but it, as you'll find out, it was had a very strong influence on Dimorphos. The companion spacecraft, Lycia Cube, it's an acronym. It's Light Italian CubeSat for imaging of asteroids. That spacecraft had 2 cameras, a narrow field and a wide field camera on board. And I think that the total number of images that it took during the mission was about 246. Okay, Gary? And this is a depiction of the spacecraft on the left, along with this CubeSat on the right-hand side. As you'll notice, the primary spacecraft on the left-hand side was an ion engine. One of the very first times that an engine of that type was used. Very similar to the engine that was used to go to the big asteroid Ceres. And what was the other one? You remember, Gary? I think, was it Pallas? Vesta, thank you very much, Jeff. But anyway, that's I think it's probably pretty much the same engine. Okay. And this, to give you an indication of how big this operation was, this is just a depiction of all the locations of the sensor, I should say, telescopes on the Earth, and not only on the Earth, but also in space. If you look at the part on the lower left-hand side, these telescopes were basically located on all the continents, including Antarctica. So it had very good coverage. And the primary one, which I'll point out, was over here in South Africa. Very key. I'll show you some information on what we got from that. Okay, and this is information that I have put together on Didymus and Dimorphos. Won't go into much too detail on this here, just to give you a few things. To give you an idea how big Dimorphos was or is, 75 meters in radius. So about 150 meters in diameter, not all that big. But like I said, when it comes to hitting the Earth, that can do a lot of damage. Because it's so small, it has a very small escape velocity, and that's good, because when you do your computations on the ejecta that really count in the momentum change are those ejecta that exceed the escape velocity. All the particles that are ejected and come back and hit don't count. So it's important. But see, what's nice about this is it's very easy to get to escape velocity, 0.19 miles per hour. That's hardly anything. So it's a fairly good setup. Okay, and this is a picture. This is actually a composite of, I think, it was a last 10 full frame pictures of Dimorphos put together. I show where the North Pole of it is, but these series of pictures that this was made out of were taken right around about 11 seconds before impact. It's a very nice, nice picture that shows a lot of detail. And I'll show you, I think, in the next one, Gary. Oh, I'm sorry, coming up later on, I'll show you. But anyway, this gives you an indication of how big it is. Good feeling. They say a picture is worth a million words. This one is comparing Dimorphos to the Eiffel Tower in France. So, and this is a superimposition of the outline of DART at the time that it hit the surface of Dimorphos. This picture that's shown here was the last full frame picture taken by DART. Let's see, if you look over, well, I give you, now this is my own scale on here. This is not exact, but I would say this is fairly close, 10 feet, give you an idea how big these objects are. But you can see how big the boulders are. There's just a lot of nothing but boulders and rocks and stuff like that. And you'll see what happened to them in a little while. Yeah, this one was taken 3 seconds before impact, but you can see that there's a lot of boulders right in that vicinity. And this is a picture that I told you about, the observatory in South Africa. This is a series of pictures that were taken from that observatory, and it shows very clearly all the debris, all the ejecta that were spewed out at the time of the impact of the DART spacecraft. You see, there's just a lot of whatever you want to call it that came out there. Hey, Gary. Okay, so I've finally gotten to the results. Just want to point out a few things here. The impact speed was about 6 kilometers per second. That's 22,000 kilometers per hour, or about 14,000 miles an hour. So that's a fairly high speed. When you think about it, that's good, because energy is equal to mass times velocity squared. So when you get a good size velocity and it's squared to get the energy, you can really increase your energy of impact very quickly. Let's see. Like I said, one of the things that we wanted to get from the mission was a feel for beta. Unfortunately, on the DART mission, we didn't have all the data that was necessary to get a precise answer, and that's going to be obtained, though, on the follow-on, which I'll cover later. But right now, based on the results, it looks as though the beta is right around about 3.61, which means that there was about 2.61 times, there's 2.61 times the amount of momentum produced by a spacecraft by the ejecta. The ejecta really enhanced the energy or the momentum that was exchanged here, and that has a lot to do with the delta V that was produced. Without that, the beta being that big, there would not have been as much of a change in either the orbit or the orbital time involved. The ejection mass was estimated to be about 1 million kilograms. That's pretty good for a spacecraft that only weight, has a mass of a little bit over 1,000 kilograms. So here are the parameters that were key: orbital period, orbital radius, orbital velocity. The results show that the orbital period changed by about 33 minutes. The key to success, or the criterion for success for this mission, was 73 seconds. Turned out to be 33 minutes. Very successful. The orbital radius was changed by about 120 feet. It did not expand the orbit, it decreased the size of the orbit by about 220 feet. The orbital velocity was changed by 2.63 millimeters per second. Now you would think that that's basically nothing. That's key. That's a very key number, and that's what's going to, save the Earth, is the delta V. Okay. Hey, Gary. Okay, and this is a depiction of the orbital change. It basically the semi-axis of the orbit. You can see that before DART hit, it was on an orbit that was farther out from Didymus, but after the impact, it came within, inside of its previous orbit by about 120 feet. Okay, Gary. Okay. So, because, prior to the impact, Dimorphos and Didymus both were tidally locked. Each one had its rotation and orbital period locked together with each other. That's now no longer the case. So what we're finding right now is there's a big fight going on. It's a physics fight. That fight is a tug of war between two asteroids that is trying to force Dimorphos back to its tidally locked state. And that's interesting. Okay, Gary. Okay, now, as I showed you, the DART spacecraft hit Dimorphos, and Dimorphos is just nothing but a rubble pile. That's a name that has been given to it, and I think is very appropriate. It's not a single rigid body. It's just composed of a lot of individual rocks, basically, with a voids in between them. And as you could have seen in the photo that I showed you before the impact, it hit in a location where there's a lot of rocks. And there's a fairly, a lot of good-sized rock boulders there. And it's been estimated that about 8% of the mass of Dimorphos was redistributed. Over 1,000 tons of material was released into space. About 2% of the boulders on the surface were released. The boulders represent about 1/10 of 1% of Dimorphos's mass. That's a lot. Doesn't sound like a lot, but it is. System was observed with the Hubble Space Telescope on December the 19th, and it took a very historic picture, which I'll show you. You can actually see the large boulders that were ejected during the impact. As I mentioned before, the escape velocity of the system, Didymus Dimorphos system, is only about, let's see, I guess that would be about 1/4 of a meter per second. The velocity relative to the center mass of the system of these objects is 30/100ths of a meter per second. So these objects have exceeded the escape velocity of the system, so they're on their own. They're no longer gravitationally bound to Dimorphos and Didymus. They're out there on their own. That's important to know. Now, what's interesting here too is the apparent magnitude of the objects in this photo I'll show you from, I think this was taken by Hubble, range from plus 26.4 to plus 27.6 magnitude, apparent magnitude. These are among the faintest objects the Hubble Space Telescope has ever imaged inside the solar system. So let's go and see. Here it is. This is another historic photograph, which I'm sure everybody on Earth has seen. Yeah, right. But you can see very clearly, this is not something where you need to have a magnifying glass. You can actually see all these bright objects around there, and those are not stars. Those are boulders that came from the ejecta that was produced in an explosion when DART spacecraft impacted Dimorphos. Now, I counted all these objects. There's supposed to be 37 boulders here, according to the scientists. I count 39. And I suspect that 2 of these dots are probably stars. But anyway, there's 37 boulders that you can see right here. Very interesting, very clear. Now, there's a follow-up on this. So let's go to the next one here. This gives you the fate of the ejecta boulders based on computer simulations. It turns out that 7.9 to 8.4% of these boulders will stay with Didymus. 5.5 to 6.1 will collide back with, collide back into Didymus, or I'm sorry, Dimorphos. But, and there's a very small percentage that are going to be continually in orbit around probably both Didymus and Dimorphos, but most of them are in an unbound orbit, which means that they have achieved the escape velocity from the system, and they're free to roam around. And what they've done is they have run their computers and found out that 6,000 years from now, and possibly 15,000 years from now, these boulders may hit Mars. Now, wouldn't it be interesting that 6,000 years from now we have a city on Mars, and the people there are using their telescopes or whatever they have at that time, and say, "Hey, we got some incoming traffic here. Run for the hills." And lo and behold, it's because of the impact of DART on Dimorphos. I thought that'd be kind of interesting. Okay, so there is a follow-on. Like I mentioned, DART did not get a good number, well, a real precise number for beta. So the European Space Agency is going to send out a follow-on spacecraft called Hera. The main objective is evaluate the kinetic impactor method for deflecting a near-Earth object that threatens to hit the Earth. And to fulfill the object, it must determine how much momentum transfer depends on the density, porosity, and characteristics of the asteroid surface and internal structure. To get beta, it needs one thing. It needs a good number on the density of Dimorphos. To get a good number on the density of Dimorphos, it needs one thing. It needs to get a good number on the mass of Dimorphos, and that's what Hera's going to do. It's going to also get the proportion of the kinetic energy that was transferred in the fragmentation and structuring of the asteroid and the kinetic energy of the ejected materials. The entire surface of Dimorphos will be mapped with a spatial resolution of a few meters, and the vicinity of the impact will be mapped with a resolution of only 10 centimeters. And the key thing, as I mentioned at the bottom, is getting the mass of Dimorphos, and it's got, actually, this is not a single spacecraft, this is 3. And let's go to the next chart. I'll show you what, well, there's a little bit more right here. Yeah, the main spacecraft is Hera, and there's two CubeSats. One's called Milani and one's Juminus. I'm not too sure how this is pronounced. I'm sure this is probably French. Juventus. I'm not too sure. Maybe it's Italian. I don't know. To me, it's Greek. But anyway.
Okay, we'll go to the next one.
I can hear again. Sort of.
And I'm just trying to get these synced together.
The volume's spotty. I can hear every once in a while.
Yeah. Here. Well, yeah, it's the station that's, I don't see why, because it's getting power from this, but anyway.
What you're saying right now is very clear.
Okay, so just stand here and give your.
Okay, so, well, okay, let's back to here.
Oh, did I move one?
Yeah,
Hang on, let me get my cursor. Where's my cursor? There it is. Let's see.
okay. So, as I mentioned earlier, when I showed you the statistics on the near-Earth objects, there's a big gap in our knowledge. There are a lot of near-Earth objects that are yet to be discovered. So, what happened was back in, let's see, when was that? Yeah, back in 2005, Congress mandated NASA to achieve specific levels of research completeness for discovering, cataloging, and categorizing dangerous asteroids. And those are asteroids larger than 140 meters in diameter, and do it by the year 2020. There's one huge problem, though. Congress mandated it, but didn't fund it.
Yeah.
So NASA was trying to figure out how are we going to do this. And what they tried to do is get this into the NASA Discovery Program. They tried in 2006, 2010, 2015, 2016, 2017, and each time they were turned down. So how they were supposed to get this done to satisfy Congress was a complete mystery to NASA, which is probably not too uncommon for Rich. I'm sorry, Jeff. Right? Won't say, okay. But, okay, so what happened was the Associate Administrator of NASA, instead of competing for money, used budget from the NASA's Planetary Defense Coordination Office. And they now have a goal to find 2/3 of the asteroids with diameters over 140 meters in 5 years, 90% in 10 years. What they have come up with is something called the Near Earth Object Surveyor. And as of October 2023, the launch is planned for September of 2027. And the picture of it that shows the concept is here. Don't ask me anything about it because I don't know anything about it. All I know is that it's probably got some telescopes on board to map out near-Earth objects.
I think that's a sunshade.
I'm sorry, what's that?
I think that's a sunshade.
Oh, yeah, that's probably, yeah, you're right. There's probably at the very top there's probably a sunshade there. But I don't know anything about the rest of the design there. But this is supposed to be in the L1 vibration point in the Earth-Moon system, which I think is located like about 1 million miles from Earth, I think. But anyway, this chart here shows the upcoming close approaches of potentially hazardous asteroids. And there's 3 of them that they're tracking, none of which are projected to hit the Earth, but they're coming very close. There's an asteroid 1999 AN10 due to have its close approach in 2027. There's an asteroid 2001 WNS due for a close approach in 2028. But the big one Apophis is going to have a very close approach in 2029, and it's going to occur on April the 13th. And guess what day of the week April the 13th is on? You got it, Friday the 13th. And guess
Is that the
how?
one- Is that the one that's gonna be between?
That's the one.
and Earth?
That's where I talked about that one. You're right. Yeah. But that's the key one. And that's going to be, that one is going to be monitored very closely by OSIRIS-REx. And for this mission, it's not going to be known as OSIRIS-REx anymore. It's going to be called OSIRIS-APEX. And what's going to happen is that when we have that very close approach, and that approach is going to be within 39,000 kilometers of the center of the Earth. Geosynchronous orbit is at 35,786 kilometers above the surface. So this is actually, I think, going to be within the geosynchronous orbit. But the closest approach is going to be over here, and it's going to be at night. And they're going to be able to see it with the naked eye. And right behind it is going to be OSIRIS-REx. And that's going to be an outstanding event. But you talk about a close shave, this is a close one right here.
How
And
big
that's,
is it?
Was Sam.
I'm sorry. Oh, what size is Apophis? I'm not too sure. I really don't know. But anyway, we have some options. If we do have a mistake that was made by the scientists that, whoops, we made a mistake, it's actually going to hit. Here's one option right here. We can run, or you have another option. This is a picture taken from When Worlds Collide. And guess who designed this rocket? I think this is a cool design, really. You know who did this? Yeah,
No, I don't remember.
Chesley Bonestell.
Oh,
Now, I thought he only did paintings. But I mean, he did a real good job on this design of the rocket. I thought, and let's look to the next chart here real quick, Gary. This is a close-up. Now, don't you think that's cool?
oh, I loved it when I was a kid.
Oh, no kidding. But that's another thing. We could have, a project led by NASA to build one of these things and then have a lottery system set up so that maybe the 100 most lucky people can actually get on board and take off and save themselves.
I'm not coming back though.
Yeah, they're not going to come back here. Hopefully, they'll find some other place to land. But anyway, that's my presentation. Thank you very much, Gary.
Okay, thank you. So my question is, we're doing this Hera thing because they didn't get a precise mass reading of okay,
Well, the reason why it wasn't done on the DART mission is because its primary mission was to test out the method of impactor, how effective an impactor would be in changing, the velocity and things.
Yeah,
of that
okay.
type.
so it fulfilled its mission and did it admirably.
That's right.
Okay, now they're saying, okay, well, how big was it to begin with? Kind of thing.
Actually, this is not an afterthought. This mission, this Hera mission has been in planning for, believe it or not, 20 years.
Okay,
They knew all along that it would take 2 missions to do the job. And they all were, it's obvious to everybody who worked on it that they knew what they wanted to get. The primary parameter is beta.
yeah,
And to get beta, you need the mass of the object that you're hitting.
Yeah.
And there was no way that you're going to get that precise measurement on one mission. You need to have, well, either you would have 2 spacecraft going on one mission, or you have one primary vehicle going on a mission first, followed by a second one. That's what we're doing on.
Yeah. Okay. So
Yes.
I just looked up the diameter. This is the average diameter. 140 meters. And the Chelyabinsk object they thought was about 75 feet.
Yeah, that's, when you're talking about things this high, you're talking about things that are not heavier than 20.
It's huge. It's gonna be 1,000.
Well, the Chelyabinsk was the largest object in near Earth's atmosphere since again in 1908. So you can imagine that, okay, we have something in 1908, we have something in 2013, about 100 years apart. You would think that maybe on average, you might have something that big in the Earth's atmosphere, let's say maybe once in 100 or 200 years. But when it comes to these bigger objects and all these objects, because you don't have the technology to get precise information for a long way off on sizes of the size of Chelyabinsk, that all these objects are going to be fairly good size. Now this is fairly small, right? You say something like about 375 feet.
No, 340 meters.
Oh, 340 meters. So that's not, that's over 1,000 feet. That's a fairly big size object. And, wouldn't that be something? And you guys have very hard, precise computer simulations or information to know that an object is not going to hit the Earth, it's going to miss by this much. We have to be, and JPL is a world leader on the ephemerides of, solar system objects. So they know, all, sizes and gravitational transients for all the objects, the big objects in the Earth or in the solar system. But, when it comes to something like that, we have the information to look at that closely. Yeah, that's another one I threw in as a backup. This goes back to 1833, and this is a depiction. Obviously, it was not a photograph at that time. It was depicting a meteor shower. It's really not a meteor shower. It's basically a meteor storm. Back at that time. And that they know are remnants from a comet, the Comet Temple Tunnel. And that shower happened about every 33 years or so, 33 and 34 years. And if you look at the history, history of the meteor showers, about that same time of year, back, in November, you'll notice that there was an increase in activity. Well, something happened recently on the last one. Well, that doesn't happen anymore. So we're missing out on a nice free show by Mother Nature. But you can just gather from a picture like that what it would have been like seeing something like that. That would have been really neat.
It was real dangerous, like fire.
Wow.
No.
Well, I guess if you were in a spaceship, but, on Earth, like I say, we're lucky. We have two oceans, and the ocean that's protecting us from things like that is the atmosphere. Now, something to think about. Here you don't even think about it because you come up with a thin atmosphere, but it's thick enough that's protecting us pretty good up to a certain point. And these are the discoveries from different surveys over the years of near-Earth asteroids. Yeah, there's 426 in.
I'm tempted to go to Europe and see it up this. The only thing is, do you really want to be?
Well, here's the risk, as it is for thinking in nature, is the weather. You just don't know in advance. Go all that way and only find out that they're having storms on that day or something.
We had someone speak to our club probably like 10 years ago. And he was doing, as an amateur astronomer, he was doing, asteroid observation. And the reason he was doing that was because, they said that, with all the new robotic cameras and stuff, they were discovering some number of new asteroids every year. But they would get like, I don't know, a small number of data points and get sort of a rough orbit. And in like 2 years or whatever, it was lost again, and they didn't know where it was anymore. And so they needed people to do follow-up observations so they could get a pretty firm, orbital elements so that they could keep track of things. So that's what he was doing. And he was encouraging other people to participate in that. And I haven't heard anything about it since then. So I assume they are keeping track of them now and that they aren't losing most of them in a few years.
A lot of these surveys, probably 90% of their observations are repeats of known objects, so they keep refining orbits.
Yeah, you see a picture like this. This is a chunk of aluminum. And what, obviously this is not under laboratory conditions, but what they did was they took a piece of plastic, and I think that it was, well, let's see, does it say? Yeah, it says about half an inch in on a side, I guess. Maybe it's like a half-inch size cube or something. But anyway, it weighed a half an ounce. And they fired it at this chunk of aluminum, 15,000 miles an hour, and that's more or less a typical speed that you would encounter with an asteroid or something. And that's the damage. And here again, if you're on the space station, you don't want to see this.
It's like a rock or something.
Yeah, you would think. Well, I don't know if it would be all that, but see, what's really important is not the material so much, but mass times the square of the velocity. So if you have a mass, wherever that one was, it probably wouldn't make too much difference what the material was. As long as you have the mass and you have the velocity, that's what's going to be in.
Yeah, I think 15,000 miles an hour probably at the slow end. Because I'm pretty sure I've read before that meteors that enter the Earth's atmosphere are usually going like 20 to 70,000 miles an hour or something like that.
So Kim, when they were that the objective when it when you said something in the dark. Oh, dark.
Yeah, they probably, yeah, you're right. The CFQ. They didn't really know in advance what kind of effect the impact was going to have. That was the reason for this test. So I'm sure there was maybe a little concern and somebody exactly what that bit the CFQ behind it. But I think that the probability of that would have been very low, almost under any condition, because of the fact that the cube was, thousands of kilometers away when it was taking these pictures. Plus, it was a small object. They had to begin with, something like 10 or something. So it's a small object, far away, very low probability of that. If there was some object coming in that direction.
Start.
Oh, there was no propellant per se. It had an ion engine, so it was not so much propellant. Once you get a spacecraft going on its way, you have a lot of different options on the propulsion system that you might have, whether it be liquid or solid or ion or whatever. I think that the ion engine probably was good for some delta. The good thing about ion engines, they last, you can fire them for a long time. So, they have a high specific impulse because they have a high exit velocity. that you can farm for a long time, even though they don't have much stress. It's the time element that's involved, so, you know, if you want to go, you know, this month, this fire for this month of time.
There's another thing, a physicist told me this, so I assume it's correct, but I don't know. He said if you have a rocket, the fastest the rocket can go is how fast the exhaust gas is coming out the back. So if the exhaust gas is coming out at 20,000 or 25,000 miles an hour, that's the fastest the rocket can accelerate to. I don't know how that's true.
With the rocket equations, so.
But he said with the ion propulsion, the ions are coming out much faster. And so if it has enough time, it can accelerate to a much higher speed.
You have to get around the head there, you look at, and you go back in history on astronauts. The very first guy that did the work on this was not Goddard, it was Tsiolkovsky, yeah. And he's even though he's called Russian, he wasn't really a Russian. He was, what was his station? You know, I can't remember. But anyway, he was the one that came up with the rocket equation. And you look at that, it's delta B equals GISP, natural logarithm of the mass ratio. At the very beginning, you have the exhaust velocity. And you can't exceed the exhaust velocity if you just look at the equation.
Okay.
Yeah. But yeah, some very, very fundamental information that's key to the development of rocketry was done early on. You know, Tsiolkovsky, followed by Goddard. And they did some outstanding work. It's just too bad that they didn't get too much recognition until a long time after they did it. Those kinds of geniuses, and it's good that we have them. You know, every once in a while we'll have a genius come along and say, you know, this is the way it really should be. And we say, yeah, thank you, Albert.
Yeah, it's gotta work out.
Yeah.
I believe for objects bound in the solar system gravitationally, about the fastest impact velocity you get is about 45 miles per second. And the Leonids are very close to that because they're moving retrograde as the Earth is moving in its orbit, so it's kind of a head-on collision.
Yeah, that's the key thing too. You know, when you draw a diagram of the Earth and orbit around the sun, and you try to figure out with respect to, let's say a comet, actually, the meteorite shower that you're seeing in the sky, you can see that if you know, let's say that you're in the northern hemisphere, for example, and you draw where the terminator is and where the sun might be in the Earth, you can see that objects that are coming, you know, towards you, you'll see them coming very fast when you're out at midnight, because you're now over the hump, and you're now after midnight, you're now going in the direction of the Earth's travel in its orbit. So all these objects that are now coming at you from the east are coming damn fast.
Early in the evening,
Yeah,
those are the ones that are catching up to me.
yeah, that's right.
We haven't gotten a meteor storm yet, but the 2000 Leonids weren't that bad. There was a while there where I was getting over 1 per second.
Well, Pleiades are the ones that you really want to look at. You know that when I was the assistant scout leader, we were taking the kid. We took them up to the San Gabriel Mountains one year. And we saw a few of them. That was really nice. But you know, the object was to draw a diagram of what you were seeing. That's not easy to do for these kids. Now, what keeps this way?
Where start they then?
Yeah, where is it? Yeah. But you know, when you see stuff like what I saw, you really think about the guys in the International Space Station. Just within the last week, they did a spacewalk out there to repair damage from objects that hit it. You know, and the thing about it, about the space station, is there's a fast rule on your probability to hit. And it has to do with the size of your vehicle. I know it's FAT, fat. Your probability equals fat. F is the flux of material that you're flying through. A is the area of your spaceship. And G is the time that you're up here. And guess what? You know, space station is the largest object up there. It's a big target.
It's been there a long time.
And it's been there for a long time. And, you know, you haven't, if you're up there for, let's say, another 100 years, you're gonna get bang for the damn good, I would think. And we were always concerned about that on the shuttle. I remember, you know, we would have flight readiness reviews. And the management was always surprised by the analysis that was done on probability hit. We always put the orbiter in a position where we would put the very important stuff protected by some good, you know, good thickness on the shuttle. But we knew there, and there were many times where the shuttle would come back, we could see hits from, not just from the, you know, a lot of times we would watch the shuttle and we'd have stuff coming from the booster separation motors hitting the external tank of the orbiter. But there were some hits there that were actually micrometeoroids. I remember one mission in particular, it kind of pretty good, like micrometeoroid in a window. But the thing of it is, those miners.
And it's realized just you.
I still remember a mathematician on the project. He came back from a meeting and he said, I got called into this meeting. Figure probabilities and stuff. He said, okay, what's the problem? Well, we've got 30,000 tiles on here. And he said, well, how many of them can you lose? I said, none. He said, you've got 30,000 single points of failure? You're insane.
Well, what's amazing about that, it's not just 30,000. It's 30,000 individually made files. No two of which were alike.
Right.
And that, I thought that was kind of stupid in a way, because you would think that you would build your ship so that perfectly symmetrical, so that you could have tiles that would match, but that was not the case. Each one was numbered, and each number had to go in a particular location.
Yep.
That's right.
Airplanes are bilaterally symmetrical, so you're gonna get a right and a left of everything.
Yeah. Yeah,
And they're different thicknesses.
yeah.
Basically, they want to contour the back surface
Yeah.
so that they can bond it well to the shuttle.
This meeting was before the first launch, and the first shuttles had a lot more tiles, because after a few launches, they decided that the upper tiles could be replaced with blankets.
And you know, each one of those had its own acronym. I don't even know what those insulations were called anymore, but you know, all these different acronyms for each of these types of insulations.
You got the tiles, you got blankets, and you got the RCC on the leading edge of the wing.
Yeah. Well, I'll tell you about the RCC. It was a big eye opener for all the engineers working on the program after we lost Columbia. Columbia was hit by insulation from the external tank on the main leading edge on the left-hand side, which is reinforced carbon. And what they did was at Huntsville, Alabama, they ran a test where they took the same size of insulation from the external tank as what hit Columbia on the left wing. They fired it at, you know, a piece of RCC from
The Enterprise.
from the Enterprise, I guess.
Yep.
And it shattered it. And they were just astounded. They could not believe
I saw the video.
Yeah. Is that something?
I'd be
That is,
expecting them to accelerate that much relative to the shuttle just
Yeah, you-
falling off the top.
see, that's the thing.
It was so
Those-
light, it
those
accelerated
pieces-
very.
The initial velocity of each one of those pieces was zero. To think that they would gather enough speed and that much momentum that they would impact so hard to break the wing leading edge was just
Not
unthinkable.
only was the piece decelerating due to atmospheric drag, the shuttle was accelerating.
Well, you know,
rapidly.
see, that's the thing that did it in. It was the acceleration of the shuttle. But it was just in a big eye opener. Everybody was just shaking their head. They couldn't believe it.
They did several shots at the leading edge of the wing. And the report that I heard was, if it had hit like less than 6 inches in any direction, they would have been fine.
Yeah, there are reinforcement ribs on the inside. You think it hit between the two of them.
I've got the videos at home.
No, until the next time.
But you look at, we had two major accidents, obviously. You look at both of them. We were concerned about the high speed turbines and high pressures in the solar producers, the high temperatures involved in the engines, the motors. The thing that did it in on both instances were non-moving, very cheap objects. An O-ring that cost 25 cents maybe.
No,
on-
That was a pretty big.
Well, government.
No, those O-rings are like this thick. They go all over here. all the
Okay,
way
so-
around that.
So maybe, okay, a couple thousand, not millions, right? Okay, but anyway, O-rings and also insulation.
Yeah.
Not moving parts, but they're supposed to be non.
And I believe the foam insulation wasn't part of the original design. That was a change later onwards.
On the external thing?
On the
originally the tanks were painted.
Well, that was over the foam, but
Yeah,
still.
don't- yeah, they always had it.
No, but I thought they were gonna have some other kind of protection up over the oxygen tank, that they went to the foam because it was light.
I don't
look
know.
back.
I don't remember.
They quit painting them the same way.
It's like 400 pounds or something like that.
Well, see, that's right, they did the same thing on Apollo. When they first had the design, paint design for the Saturn V, they had these, typically on a launch vehicle, you put black markings on there to check the roll. They took a lot of those black markings off because it would save weight on the launch vehicle. Yeah. Weight, actually, I'm sorry, paint actually has weight.
Oh, yes,
Yeah, something that big.
even airplanes,
Yeah.
commercial airplanes,
American
they have
Airlines
to
was
weigh
famous
it for the weight of the paint.
Yeah, it's.
Give you a ticket discount if you buy an anchor.
Take off the clothes, will save some weight. Amazing.
So people
Yeah, I guess, from what I talked to Gary, I was wrong. About
Stop recording the cloud.
Space.
Not yet.
Okay.
Here
it goes. We're on slide 97 of 144, but since we have to leave the building, this will be it. So we thank everyone for their time and attention.